Hey, differential equations. Okay, we're moving on to lesson 27, Laplace transforms. But before we talk about Laplace transforms, let's just define an operator. An operator is a mathematical device that transforms one function into another. So you can think of it as derivatives are an operator, and integrals are an operator. It's transferring one function into another function. And so now we're going to talk about a very specific type of operator called a Laplace transform. And so it is a useful tool for solving differential equations with constant coefficients. So it's another way of solving these types of problems that we've been solving. And so basically we're doing this in 3 steps. We're going to be given a hard differential equation, and so using Laplace transforms, we're going to actually transform it into an algebraic expression. And then we can solve that algebraic expression. And then from the solved algebraic expression, we can do an inverse transform. We can undo it and then find our solution. And so before we get into how to solve, let's practice for a while transforming things using that Laplace transform. The book really doesn't do a whole lot with this, and so that's why I've included this other worksheet for you to practice doing that transformation. Lesson 27, Part 1, Laplace transforms. So before we talk about how to use the Laplace transforms, let's go ahead and find the definition. So Laplace transforms are used with the capital italicized L. It can use either the bracket, or it can also use the squiggly bracket. So the square bracket or the squiggly bracket, they are the same thing. And then notice we're putting a lowercase f of x into here. That'll become important. And it is defined as the integral from 0 to infinity of e to the negative sx times whatever function you want to put into it, dx. Okay, and then when you plug that out, when it gets transformed, then the lowercase f turns into a capital F. And so you put in a lowercase x, or you put in a lowercase f with an input of x, or sometimes the input is t very commonly. The book uses x, but a lot of other places use t. And so then when you get done, you get a capital F with the input of s. Okay, so let's go ahead and do one. Let's go ahead and do just really, really simple. Let's start with the simplest case. Let's find the Laplace transform of 1. And so this would be the integral from 0 to infinity of e to the negative sx times 1 dx. This is an improper integral, so we have to take a limit. Yay! So the limit as b goes to infinity of the integral from 0 to b of e to the negative sx, that's an s, f of x. So continuing on, we've got now the limit as b goes to infinity of e to the negative sx over negative s when we find that integral evaluated from 0 to b. So writing that out, that becomes the integral as b goes to infinity of e to the negative sb over negative s minus e to the negative s times 0 over negative s. So now as we take that limit, as this goes to infinity, it's a negative power, so this goes to 0. And if you have 0 as your power, that means that that numerator goes to 1. So then as we take the limit, we find that our Laplace transforms 1 into 1 over s. That's an S. Okay, let's do something a little bit more complicated. Not a whole lot more complicated, but a little more complicated. Let's do the Laplace transform of x. So then integral from 0 to infinity of e to the negative sx times x dx. Again, it is a improper integral, so we have to take our limit as b goes to infinity of the integral from 0 to b of e to the negative sx times x dx. Okay, so in order to find this integral, we're going to have to use integration by parts. And so our integration by parts says that our u is going to be x, which means our du is dx. dv is e to the negative sx dx, which means v is going to be e to the negative sx over negative 5. Okay, so actually finding that integral means we have limit as b goes to infinity of, so remember integration by parts, u v minus integral v du. So we've got x times e to the negative sx over negative s integrated from 0 to b minus the integral of e to the negative sx over negative s. But the nice part is my du is just dx. Okay. To the next one, I'm not going to plug it in yet. So limit as b goes to infinity of e to the negative sx over negative s minus e to the negative sx now over a positive s squared. And we have to evaluate both of those from 0 to b. So plugging those in, now we've got limit as b goes to infinity of, remember we're plugging in for x, so this becomes b e to the negative sb over negative s minus 0 e to the negative s times 0 over negative s minus e to the negative sb over s squared minus e to the negative s times 0 over s squared. Whew, okay. So as we take this limit, this power means that that term is going to go to 0, so that entire term goes to 0. This power means that that's going to go to 1, but we've got this other 0 here, so 0 times 1 is going to be 0. As this goes to infinity, this thing's going to go to, well, this term's going to go to 0. And as we go to infinity, this term's going to go to 1, so we've got a negative 1 over s squared. So now, minus the negative means that my Laplace transform says that when I do the Laplace transform of x, we get 1 over s squared. Okay, let's talk for a moment about properties. So kind of mashing a couple of properties together, if I take the Laplace transform of some constant times a function plus or minus another constant times a different function, then first thing I can do is I can pull out those constants and do the Laplace transform just on the function. The second thing is I can add or subtract those Laplace transforms, or I can do the Laplace transforms first and then add or subtract the results. So for example, if I did the Laplace transform of 3t plus 4, well, we just said that the Laplace transform of t was 1 over s squared, and we did the Laplace transform of 1 is 1 over s. So I could rewrite this as 3 times the Laplace transform of t, which would be 1 over s squared, and plus 4 times the Laplace transform of 1, which would be 1 over s. And so then pretty straightforwardly, I could see that this would get transformed into this. That would be my answer. And because these Laplace transforms, because of this property, then while you can do those integrals every single time, then it is a lot easier just to go from tables.